Okay, having spammed out a whole lot of quadratic algebra, I just want to mention a quick area of application just for fun. Something I stumbled upon in a video from the guy who actually made this animation engine, so credit to his work. Sorry, no APA. I have no expertise in this field, or indeed in anything remotely related to real life, but apparently there's this technique called ray tracing, used in making animated movies. As you can maybe see there, it's to do with how we, as viewers, are seeing objects through a screen, and the way we mathematically model that is by imagining some sort of camera shooting out all these rays through the screen at the object, and analysing this setup apparently helps the animators realistically draw and colour their objects and their relationship to the light source and all that stuff. So, we can simplify it by going 2D just to illustrate. Just maybe in practice it's a sphere or something instead of a circle, but algebraically it's pretty much the same thing. So you imagine that all these rays are coming out, and we want to think about where and how they're hitting this object. You see some of these rays pass through, with each one hitting the object twice. Some might completely miss, and a few might just hit it with a glancing blow like that. I call that a tangent to the circle. And if you're spelling something close to the sorts of equations we've been solving, it's actually exactly that. This is all equivalent to how quadratic equations can have two real solutions, or sometimes none at all, or sometimes just the single distinct one. But why would this setup even be quadratic? Well, you might remember from before, but don't worry if you don't, that the equation of a circle looks somewhat like this. It's based on Pythagoras. And really in 3D, it's pretty much the same, but with x, y, and z, not just x and y. And shooting out a bunch of straight lines gives a bunch of equations of this form. There's a gradient and a y-intercept and all that. But the important thing is, if you're trying to detect where the lines hit the sphere or circle or whatever, you're looking for where both equations are true at the same time, something we called simultaneous equations. And one way to make that happen is to substitute this expression for y into the equation, giving this. And now we won't go any further with this, but you can see that it gives exactly what we were expecting and what we've been doing, a quadratic equation. You see the squares there. Okay, so it's interesting. A bloke from Pixar apparently said that one of the movies they made recently was estimated to have invoked the quadratic formula in this process around 1 trillion times, which is a lot of quadratic formula. So, we're going to bring back a general quadratic equation, as well as the quadratic formula, and see if we can pull from it, in a quick and reasonably efficient manner, the answer to that question: how many solutions does some given quadratic equation have? We've seen it's either 0 or 1 or 2, so the aim of the remainder of this video is to see a quick and easy way to find out how many real solutions a quadratic equation has. Okay, so why were there possibly multiple answers in the first place? Well, I think we blame this plus or minus symbol for that. Okay, so because it's plus or minus this big root guy here, we have seen how we can get two answers, one option for the plus, one option for the minus. So if that's the one to blame, then maybe we can get some information out of just looking at the b squared minus 4ac. Now notice we're only looking at the number inside the root, we're not bringing the root along. We use this symbol for the number and call it the discriminant, as per the title of this video. And there are naturally three cases for how this number could behave. It could be positive, it could be 0, or it could be negative. In the first case, if it is positive, that means the plus or minus has full effect. You have your two options from adding or subtracting the square root of this number, and so both of these guys give you valid, different real solutions, and we would end up with two real solutions. In the second case, if this number equals 0, then we're doing plus or minus, well, nothing, which means our two solutions above just look like that, and so we can see that both our answers are actually equal to the same number, and we only end up with one real solution. But just a disclaimer there, we say 1 because there's only one distinct number, but in some contexts later on we actually still insist there are two solutions, only that they just happen to be the same number, which I know feels weird, but that is important in making some other ideas consistent. So we say there is only one solution, but as you can see, there's sort of still two, only they are equal to each other. Okay, in the last case, the discriminant could be less than 0. That means the guy living inside the square root is a negative number, and we know that launches you into the complex world, restricted to just the real numbers. That is something impossible, and so we have no real solutions. So in practice, if you want to check how many real solutions a quadratic equation has, you don't need to pull out the whole formula, you just need to calculate this b squared minus 4ac guy and see if it's positive, 0, or negative. If positive, you have 2. If 0, you have 1. If negative, you have none. Okay, so let's end with an example. We have a ball thrown with its height modelled by a quadratic, and we want to know if it hits the ceiling, which is 3 meters off the ground. So while we haven't done graphing yet, you've probably seen that such an equation produces a parabolic arc like this. And the question is whether the 3-meter ceiling is so low that the ball hits it like this, or maybe just grazes it, or maybe the ball misses the ceiling altogether and can fly freely across the room. So to investigate that, we should put 3 into the h, the height of the ball, in the equation. And now the question is whether there are any real solutions to this, because such solutions would correspond to points in time where the ball hits the 3-meter high ceiling. As normal, the best way to start a quadratic equation is to get a 0 on one side, so we're just going to subtract the 3, turning the plus 1 into a minus 2. Often things just feel better if the first term is positive, so we might also just flip the sign of everything. And then to count how many real solutions this has, we use our discriminant, which again was the b squared minus 4ac guy, the thing that would sit inside the square root if we were to use the formula. So to calculate him, we start, as usual, by pinpointing our a, b, and c, which are just the coefficients from the t squared down to the constant. We start by doing b squared. So the whole negative 6 goes in there, don't forget the brackets. Then it's minus 4 times a times c, so we can pop in the 5 and 2 in place of a and c there. This works out to be negative 4. But really, we don't care what the number is, we only care that it is a negative number, which corresponds to the case of, well, complex answers, or in other words, no real solutions. And since there are no real solutions, the conclusion must be that the ball does not hit the ceiling at all, and we are done. So this is really just an efficiency trick in pulling out of the part of the quadratic formula, the stuff that deals with possibly multiple answers. And just by investigating that number, you can quickly count the number of real solutions to quadratic equations. Okay, thanks for watching. That's all for now. See you around.